All right, guys, today what we're going to take a look at is the last part of Chapter 5, Triangle Inequalities. Okay, so first I wanted us to do a little exploration here. I asked everybody in the class, can you draw an obtuse scalene triangle? So obtuse would be something like this, and I want to make sure none of the sides are the same. So something like that. And then I say, grab a ruler, grab a protractor, and can you find the largest side? Can you find the largest angle? And what you'll find is that this is the largest side, and this is the largest angle. And what we'd all notice is everyone would wind up in the same position, which is they're across from each other. So we can extend this to saying that the smallest angle should be associated with the shortest side. So these are the theorems that we would want to write down about this. If one side of a triangle is longer than another, then the opposite angle must be larger than the other. If one angle of a triangle is larger than another, then the side opposite the larger angle is going to be longer than the side opposite the smaller angle. Let's think about what we need to make a triangle. You need three sides, right? Does that mean any three sides can make a triangle? Of course not. There must be some constraints, right? If I go like this, not a triangle, right? That side was too short, okay? We're also going to say that you can't do this, right? Like that's not a triangle. Like this part of it is, sure, but just extending this side all the way through, it's too long, right? Not a triangle. This is the triangle inequality. The idea that not every group of three can form a triangle. There must be a certain relationship. Before I explain the relationship, let's address this idea. The shortest distance between 2 points is always a straight line, meaning if I give you this point and I give you this point, the shortest distance is this. Not going up here first and then down. I always kind of say, like, I mean, think about it this way, right? If I told you, what's faster, taking a boat across the river or walking up to this bridge and then walking over the bridge? You'd be like, the boat. Just go straight across, right? So we can extend this into a theorem, right? That this side, we'll call it x, should always be a shorter distance than the other two sides. And that should then apply, like, shouldn't that also apply that to go from here to here, B should be shorter than the other two? Oh, and A should be shorter than the other two. So that's my idea here, that because the shortest distance between 2 points is a straight line, all three of those things have to work. If even one of them does not, it's over. The gig's up. No triangle. All right. Now, what does this look like in a problem? How does this get challenging? Is that I'll give you basically two constraints, right? So here's the constraints. You have a side of 12. You have a side of 8. And I say, what's the possible range for that third side? Because there's more than one piece that I could use there. If you think about it, this is the hinge theorem that we've talked about before, right? That we have, this is like, saying this is why side angle side, right? I don't know the angle. I just have side side right now. So obviously, there's this range of like not all these triangles are clearly not congruent, but what they do have is the fixed sides. So what does the fixed side tell me? What can I do with the fact that those sides are fixed? Well, what I know is that there's a shortest possible value, right? Before eventually I run out of room, right? Where if this is 12 and this is 8, no matter how close together I get, right, there's an idea that there's got to be a shortest possible side there. Got to be, right? And then there's got to be a largest possible side. There's got to be a largest possible side, meaning there's got to be a space where at a certain point I've just overstretched it. Where even if I say that this is 12 and this is 8, if I go much further, I'll be destroying the integrity of the shape. Okay. So how do I actually set it up and like solve that problem? We use inequalities. We can see it here. So the idea is you need to set up 2. That's, I think, people do a really good job with, like, they'll either think of this one, like, oh, sure, okay, Mr. Carr, like, if I'm going with the inequalities, then I know, like, if x is really small, I need to make sure that the 2 smallest sides together are still bigger than the third side, right? X plus 8 still needs to be bigger than 12 because 12 needs to be the shortest possible distance here, right? The second that x becomes something like 3 plus 8 is 11, and that would imply that it's shorter to go this way than directly between the 2 points, which, as we discussed, definitely not true. And therefore, I could just subtract 8 from both sides. All right, x needs to be bigger than 4. Same thing over here, except I need to think about the inverse. What if it's these two, the sides that I already have? What if those are the short ones? I need to make sure that when I add 12 and 8 together, that that's still bigger than the other side. Because if the second this becomes 22, right now the implication again is that it's actually shorter to go this way than it is to go right in between the two. And then I got to combine the pieces together. So x has to be bigger than 4, but it's also got to be less than 20. So it looks something like this. X is in between 4 and 20. Okay. This is the last new thing that we're really talking about in this chapter, which is good. We've done a lot of cool stuff, learned a lot of new things, taken a deeper dive into triangles. So hopefully this video helps with reviewing the lesson and tonight's homework.